Alright, time for another draft science video presentation. So we're going to talk about kinetic energy in the context of the last couple of videos, which are sort of an overview of how physics you don't need to provide, although I am providing one, a rational, decent, simple model to explain the physical universe. You don't need a replacement for their theory. To recognize that their theory is really bad physics. It's bad science. Really bad science. Not just a little bit bad, but I mean really bad. And on every single subject. The whole gravity bent space thing, no evidence really. No good evidence. Kinetic energy, which I'm going to talk about now, terrible. Just a horrible, awful history. If you go looking to find out where this came from and why people believed it, none of the reasoning is good. The logic is terrible. All right, and then photons, where overtly they have pretty much lied for 200 years about the similarity between water waves or sound waves and what light does, when there are not all of these similarities in any of the details. And you don't have to. We're not talking about going, using an electron microscope to analyze details. We're talking about details that are right there, like the pattern matching, like the fact that the double slit pattern is creating two patterns. Just simple facts like that. Lies about experiments that never were conducted, telling us what the conclusion of those never performed experiments are, and therefore using that as an argument, as a proof. I mean, real horrible violations of any kind of notion of a fair trial. If you watched like a court TV or something and you watched lawyers performing as badly as these physicists, you'd be outraged and you'd be saying, why are they allowing that? Why is all this shenanigans? This shouldn't be allowed, shenanigans. This is important stuff. A man's life is dependent on this outcome. What do you mean? He can just make up evidence? He can just knock evidence off the table? He can just pretend, oh, it's a vector, it's a scalar, it's, we don't know where the energy's going. I mean, they do this in the kinetic energy argument, okay? So one of the arguments is they'll pretend when they're calculating their kinetic energy that it's somehow not in a direction and it's nothing like momentum. It's completely a different thing. Momentum is in one direction and somehow kinetic energy is who knows where. So, I mean, a train going down the track, somehow we're confused about what direction it's going to have an impact on, where we're going to measure its energy. Maybe we're going to measure it at the front end, or no, we'll measure it at the caboose, or we'll measure it at the stands next to the train and watch it go by and then say, gee, it doesn't have any energy because it didn't knock me over or anything. I mean, because we're totally confused. We don't know where it's going. Where's the energy going? It doesn't have any direction. I mean, it's that outrageously bad as logic. Absolutely no logical reason to contrive some nonsense that kinetic energy is in any direction and momentum's only in one direction. No reason. Too stupid. And yet they get away with it. And why they get away with it is because I guess people just I can't make any sense of it. You think you're smart people, you're arrogant as fuck, you're all telling me what the truth is. Well, what the hell's the reasoning? There's no reasoning to defend that nonsense. Why haven't you raised your hand and say, I don't think that's quite right? I don't think you can do that. I don't think you can pretend it's a completely different thing when it's pretty much the same exact thing, same exact rules, kinetic energy, momentum, same rules. Yeah. And it's overt. In the case of like a gun, they'll say Newton was right. Newton, third law, really important law. Yes, we figured out some stuff. It's really good we figured this out. Let's just violate it completely. Okay, with the proposition that we fire a gun and 2,000 joules of energy goes this way and 2 joules of energy goes that way. Yet we'll say there's an equal and opposite reaction or action. Action equal opposite reaction. We'll say crap like that, and it's obviously just crap. Because you're saying there's 2,000 joules of energy going one way, and there's only 2 going the other way. How can you have a third law? How could the third law mean anything? If Newton was wrong about momentum being the truth, I mean, being the actual way you measure a force, and therefore measure energy, then if you think Newton was wrong about that, you might as well throw out that third law, because it doesn't make any sense. It doesn't mean anything anymore. Obviously, you're violating it all over the place. So, I'm totally disengaged from having the conversation, because I'm saying, what, you people are so dishonest that you won't even concede these points? You're that dishonest, that you won't concede? All right, so if you research the history, okay, so this is what we're debating. All right, so in 1652, or whatever the year would be, some kind of silly year, way back, even actually a year before Newton published his most famous work, the Principia, telling us all of these great facts about reality, the year before that, a guy called Leibniz, proposed that the universe really didn't run on this mv stuff, and that the real stuff was mv squared, that if you want to know what the energy of something is, this is how you did it. And it wasn't until 100 years later they added a 1/2 in front of it. Because guess what? The physicists, the scientists, the engineers, they figured out this really isn't right. This makes no sense at all. See, if you just use this, then the bullet has 4,000 joules, and the gun gets 2, right? And so they figured out that's got to be way off. So they cut it down to 2,000 instead. Yeah, it's not much of an improvement, but I'm just saying they figured out something, so give them some credit that they figured out this number was insanely silly. This number says that the 8-pound bowling ball going half the speed of a 16-pound bowling ball knocks down 4 times as many pins. Too silly, right? So anyway, this is the form that it started in. Now, it was proposed before Newton, and everybody hated it, pretty much. Nobody paid any attention. Leibniz was buried as kind of a loser. He just happened to be notorious in the sense that he was accused, and I think probably realistically, if you actually go through the history, of basically stealing Newton's idea of calculus. Now, he reformed it, he put it in a different shape and he used different symbols, but he basically got the idea, clearly he got the idea from Newton. And because Newton had already written it, before Leibniz, and the papers were accessible to Leibniz. Leibniz visited Newton. Newton has papers all over the place, probably let him sleep over for the night, blah, 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 blah. Anyway. So it's a realistic that, yes, it's proven that Newton had the idea first. And so the only real question is, did Leibniz pretend he thought of it too? All by himself. Pretty unrealistic. So anyway, this is Newton's worst enemy in life, caused him all kinds of grief. Because, Newton had to say, hey, wait a minute, I already thought of that 20 years ago. Here's the proof. I sent letters to people and stuff. Anyway. All right, so it starts with, and Leibniz is quoted as saying, now this isn't an exact quote, but it's pretty close. Newtonian physics, or he used Descartes as an example. So this is, like I said, before Newton pretty much published a paper validating everything Descartes said. So he was attacking Descartes, who believed in just MV. You want to know something's energy, you just ask the simple question, how much mass does it have, and is it coming right for you? At what speed? The faster it's going, the mass, the more trouble you're in. The slower it's going, the less trouble you're in. Very simple. And it certainly makes the equal and opposite reaction thing make a lot more sense. Anyway, so this is Descartes and Newton. This is called the quantity of motion. It's just, you're just saying how much motion does it have and how much mass does it have. Now, so saying quantity of motion doesn't really get to it, right? Because you have to include the mass. But anyway, it's energy. They didn't have the word energy then, but that's what they were saying. This is its energy. This, you want to know what a force is going to do? This is what it's going to do. Anyway, all right, so Leibniz proposes this crap. It isn't really accepted by anybody. Everybody makes Newton into a god for getting right answers, and this is sort of ignored because none of Newton's physics works if you're paying attention to this, right? If you think mv squared works, then you think Newton misidentified the functions in the universe, and he didn't predict Halley's Comet. He didn't predict the motion of the stars and the planets and all the rest of the crap. I don't know if he did stars, frankly. But anyway, he'd have to get all of that crap wrong because this formula is going to get very different answers than this formula. So clearly Newton got right answers, and clearly this seemed like the man kind of thing here. This works, so why mess with it? All right. So in his Principia, Newton publishes a formula, okay, F, the force, equals the change in your momentum, okay, that's your mass and your velocity. Let's put mass times velocity just to be clear. It's not very complicated. Change in your mv, okay, over time. And all that really means is that the unit of time can be anything. So you're saying total change. So this is a total here. All right, this number is your total change in momentum. So something hits you, you start rolling 2 miles an hour in a direction. Well, you're taking the change in your momentum, which is the 2 miles an hour because your weight didn't change. And now you're just saying that is basically the force. That's what the force did to you. That's how much of the force you consumed. So you want to know how much force acted on you? You just look and see how much either your mass or your velocity changed, right? And your mass isn't going to change. So obviously forces don't change your mass. So obviously your velocity changes. So your change in your velocity will be the force, pretty much. And the time just means, well, if I take the total and it's 15 seconds, I can know if I put 1 second in here, well, then it's 15 into this total. Now, I could use minutes, I could use hours, or I could just say, what's the total time of the event? The total time of the event is 15 seconds, so I'll make that 1 unit. And so then I just put a 1 here. And obviously, if I put a 1 here in the bottom of the fraction, I can just get rid of the fraction. It doesn't mean anything. So clearly, Newton was saying force equals mv. Now, that's a rational derivative. Right, all I got rid of was this, right? Because the time is not relevant. I don't need to know the force per second. I don't need to know the force per minute. I just want to know what's the total amount of force. I don't know, do you care if you're looking at a bathtub, do you care how much water is going in per second, or you just care about how many gallons of water is it? That's all that matters, right? So you're just saying, well, let's use that as the unit, and we'll understand that the amount of water I poured in will equal the amount of change in the bathtub. Duh. Couldn't get a simpler derivative. Force equals momentum. Clearly. So anyway. And so what did they turn this into? They said Newton said F equals ma. Okay, now Newton never said that. So Newton didn't say mass equals mass times acceleration. And what do they do with acceleration? Well, they make it one of these special things that has a vector. We don't know which way the acceleration is. We're confused. So one train hits another train on a train track, and we're going to be confused about which direction the acceleration is going to be in. I don't think we're going to be confused. Okay, I don't think there's any confusion. So they use this as an excuse to make acceleration into some sort of dot product. It just has a vector of direction, and they go through all this massaging, as they call it, of these figures to sit there and come up with this silly 1/2 mv squared. All right, and say this, force equals your change in momentum, Newton's equation, equals this. That somehow this is what Newton was really saying, when obviously it's not what Newton was saying, and you're just lying, okay? I mean, you're lying about Newton. You're lying about his intent. You're lying about his logic. You're lying about his physics. You're lying about it to say this is what Newton intended you to believe, when this was invented by Newton's worst enemy in life. That's how bad their distortions have become. They need to validate all of this crap. So they try to validate it by putting somebody nice person's name on it. Just like they put Einstein's name on gravitational lensing, even though he said there's no such thing. And then they put his name on an Einstein ring, even though he said you'll never see one. So they just keep ignoring what Einstein actually said and just keep putting his name on a bunch of crap he would be totally opposed to. Schrodinger has been labeled with all kinds of mystique about all of this entanglement and superposition when he spoke aggressively against those belief systems. He hated that physics. He didn't just dislike it, he hated it. And so it's so ironic that they're stealing these prestigious names who have done good things in physics and applying their name to this shenanigans, this obvious massaging to force things to fit. Okay, not because they naturally come out of the evidence. They won't, none of this comes naturally out of anything called evidence. Quite logically, Leibniz had no physical evidence to defend mv squared. He could just say something like, bullets go fast. Gun barrels go slow. Something, almost ridiculous in the sense of it having no real measured values, no science, okay, to defend it. All right. So do I need to go any further with Leibniz? No. So I need to erase. So I need to pause. I'll be back. All right, I'm back. Bigger and better. Anyway, so moving on now. All right, so mv it was mv squared. Let's understand. So it was mv squared. So we know that this is the 4 times, okay, formula. That's the state of the kinetic energy formula at this time, all right? So we're talking about the end of the 1600s. This is what the kinetic energy formula was. And so it got really, really outrageously wrong answers. If you used it today, I mean, there would be really bad answers. 100% bad. You say 100, the answer's 200. You say, 50, the answer's 100. That kind of thing. Way off. All right, and so in the 1720s or somewhere, this Madame Châtelet or whatever, some French aristocrat, exceedingly wealthy type. Anyway, she gets interested in the subject. She thinks Newton's brilliant, yet, okay, it needs editing. She's also intrigued by Leibniz's formulation of energy. Now, whether the appeal is that Leibniz was a believer in, he was aggressively human centric, okay, aggressively a lover of humanity and a lover of us being special and God possessed, and life exists in a little tiny, he was a Horton here's a who believer. He believed that there was souls inside of the everything, because God wouldn't make anything without a soul in it. That kind of crap. So whether the appeal might have been some of those philosophical connections. I mean, I think she would have been basically a Darwinian atheist, but she certainly would have had a bag of crystals in her pocket. She was a free willer, that kind of stuff. She believed we were all to be doing some sort of magical fun stuff. She got what she deserved, since she died having a baby. So, yeah, brilliant at 40. Anyway, I don't want to get into the politics of it. But it's sort of important, okay? It's sort of important to recognize Hitler was a vegetarian, okay? But obviously an insane imbecile. Anyway, and the two don't have anything to do with each other. They don't have to have anything to do with each other. But anyway, these things you do have to measure motivations. And you say if they could be that wacky on one subject, then maybe they're just making crap up on the other. They don't really have there's no integrity behind her appeal So whatever appeal she saw in this, or however she manifested Newton's failure, Newton got all these right answers with MV, and yet somehow she thought there must be something wrong with it. And you'd say, why did she think that? There's no really good reason to think it. There just isn't any good reasoning. So why are they trying to force the physics to fit some other model? You have to ask the question, because there really wasn't any reason. There wasn't any experiment that sat right there in front of you and said, I have to come up with a different formalization because this one doesn't work. There was just nothing in real life that give you any indication that MV wasn't working. So look, anyway, so she hooked on it, and then she started researching it. And so what she found was there was another scientist who was pursuing some sort of similar notions that maybe Leibniz was right, and so he was doing clay experiments. Now, you know, it shouldn't take a whole lot of great scientific thought to figure out that if we're using a block of clay and saying how far does something go into the clay, that maybe how we change, you know, how we formulate the clay. There's all kinds of different clays. There's really stiff clay, really soft, lumpy, soft clay. I can pretty much just manufacture whatever answer I want by how I make the clay. And as I've pointed out, I can take cornstarch and make a kind of gooey clay out of it, and it'll give me exactly the opposite answer. It'll say that it's Vm squared. Okay, it'll give me exactly the opposite answer. It'll tell me that mass is much more important than velocity. Okay, because the faster something goes, the less it'll penetrate, and the slower it goes, the more it'll penetrate. You know, so I'll get some kind of opposite formula by just changing the formula of the clay. So it's a really bad things to use for the experiment. And as I've explained, you can understand why fast things would penetrate certain objects. And that you can't measure how you're acquiring friction, because friction is variable. The faster you go, the less friction you'll encounter, because the faster you go, the more likely it is you're just tearing atoms. Lots of things change. The thermodynamics of every substance changes as you increase the velocity. Like breaking a piece of wood, you know, the karate guys, by increasing the velocity, they decrease the amount of energy they have to use to break the wood, because the fibers they don't have time to react to the energy, therefore they can't absorb it, and they snap instead of bending. And so if you can cause things to snap instead of bending, you can make something move a lot faster or a lot further through it. So this isn't, again, now, is this really, really complex physics I'm explaining? Like, this is a detail that only the most brilliant minds in the history of mankind could figure out, that some substances have a bias against velocity or a bias for velocity, that the faster you go, the further you go, versus, you know, much further. You know, that the friction isn't applied evenly to all objects, because the faster objects incur less friction. You could see it even on a road. Like, say if I had a road with just a couple little tiny bumps in it, you could argue that a fast thing hits one bump, goes airborne, and just flies over the rest of the friction. You know, I mean, simple little arguments can be made about how speed changes how friction absorbs energy, and it absorbs it. Friction isn't a force, it isn't a counter force. Friction is just you having energy, you know, a certain amount of velocity, and you're giving it to other things. The friction is you giving away your velocity. It's not applying an opposite force of some kind. It's you giving your velocity to it. It touches you, you give it some of your velocity. It touches you, you give it some of its velocity. You're giving it your energy. It's not providing any energy. So they make friction into a force. The friction force. It's actually a force in their model of the universe. They've turned friction into a force, when clearly all friction is you know, if you're going to use that kind of logic, you just say that when a bowling ball hits a bowling pin, what we should be saying is the pin applied a force to the bowling ball called friction. No, it didn't. Clearly what happened is the ball hits the pin, it gives the pin some of its velocity, and this has less velocity because of the interaction. It gives it a portion of its energy. This has a certain amount of energy, It gives whatever 0.33% of it to this pin, shooting it in a direction, and now the bowling ball has only 66% of its velocity remaining. It's energy. Yeah, that's what you don't call this friction. You don't call hitting a bowling pin, oh, there's the force of friction being applied to the ball. Come on. But you know it's exactly the same thing as the little pins the ball is hitting when it's rolling down the alley. All of the interactions, anything hitting something else, is a exchange of the energy. And you don't call this, okay, I mean, you don't call the one that's draining your energy this way a force, and then call this one just a pin. No logic here. I'm sorry, this is not logical. And physics students should have been way above falling for this crap. All right. Now, they're not told this history, so you have to cut them some slack. I've seen no college professor ever explain the origins of this dopey theory. All right, so anyway, so the French woman promoted this heavily, okay, because she had these clay experiments, and she did a couple other experiments dropping things in water. Those haven't even been close to being repeatable, so I don't know if anybody who's repeated any of those experiments. But obviously the clay experiments, you can't repeat them because you don't know what clay she used. So depending on what clay you use, you'll get a different answer. All right. So, but the point is that she could show, okay, that she could drop two objects, one from 4 times as high. I should make this, okay, and she could show this dramatic result that the one dropped from the higher point, went much deeper into the clay than the one, dropped from the lower point, blah, 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 blah. And the argument is this only has 2x the velocity. You have to go 4 times higher to double your velocity, because that's how gravity works, because it works on your mass, and it depends on the time you're in it. It's like a rain, it falls. So these two objects, this one will only take twice as long. So even though it's 4 times as high, it'll only take it twice as long to get here. So it's only in the gravity twice as long, and therefore it only has twice the velocity increase. And this is all stuff logically understood. And twice the velocity and the same mass, you could argue it has twice the energy. And you'll know that because you'll have an impact and blah, 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 blah. But doing it with clay, this could have a huge bias for velocity. And if I can make it go even faster, I could get it through the clay even faster and more dramatically. So it's obviously not a very good measuring instrument. This isn't like some kind of perfect thermometer using up a lump of clay. And that flaw, is just a glaring flaw. It's not, a little flaw. It's a glaring flaw. This isn't a very good way to measure energy. Okay. So anyway, she got away with it, and it was accepted for 100 years. People started migrating to the MV. Again, she was defending MV, okay, which at the time, you have to concede by your modern standards, this was like they would say to you the answer is 100 joules. And by your modern formula, no, the answer is 50 joules. I mean, that's how far off it is. It's not, it's not close at all to being the truth. And yet they were all certain they proved it. They all certain it was well evidenced. Yet they didn't have a whole bunch of evidence. It doesn't make any logical sense. Again, it violates Newton's third law. So what's the point of having that? All right, well, anyway, so in the 1800s, they invented the word energy, and they started reformulating this derivative. They just started turning it into a Newton derivative by doing the F equals ma thing instead of the F equals changing your momentum over change in time. So by doing this F equals ma thing, they contrived a formula where they can figure out how to sit there and modify this formula to get a 1/2 in front of it. mv squared. All right, and so the derivative is, in my opinion, just a nonsense based on their definition of what a force is. They think a force, no, they think work. Okay, work is force times distance. So they're basically saying that we only care about how you take the energy away from something. Distance just has to do with friction, right? without friction, everything goes the same distance. So, how could that matter? And you would obviously know that things that are going faster are going to go more distance, right? And any applied force to take that distance away is going to do the inverse of what gravity does, in the sense that you're only applying a little bit of, you're only knocking down things at a certain rate, and so the fast thing will take longer to, any amount of time. You can understand the fast thing is going to go more distance than the slow thing, but it's not going to be proportional to its actual energy. So distance isn't a way to measure energy. You measure energy based on how much time. But anyway, this is what they said work was. It only mattered how far you went. Okay, it doesn't. There's no other standard. So, and I'm just saying it's kind of a silly definition of your actual work, and so they use that to contrive this. But anyway, I don't want to get into that much detail. Beyond the fact that I just want to say, there's no physical evidence. So they didn't have any experiment that demonstrates this to be true. All right, so they just decided it's true. Okay, because, and that's it. Because they can't point right now in the modern era. You still can't point to an experiment and say, look, that experiment demonstrates it. Now, Stephen Bro thinks he's providing the evidence, but I mean, you'd have to assume that if it's never been done before and Stephen did it for the first time, that maybe there's something wrong with how he did it rather than the fact that he actually accomplished anything. All right, so now we'll just go through some of those details about what experiments there are that could possibly give us some insight about whether or not this is true. Now, I would argue that no spaceship can use this formula and navigate space, because it's basically saying that it takes me a certain amount of energy to shoot a dime out of one side of my ship, or to shoot 2 kilograms out of the other side. So 1,000 times difference in the weight. And the simple argument is the same explosion will create, 1,000 miles per hour velocity here and only 1 mile per hour velocity here. All right. And the truth is that works. The fact is that this is the same amount of joules going this way as there are going this way, and that your spaceship will keep going straight. If you do this event, you will create just as much thrust, okay, in this direction as you will create thrust in this direction. A dime going 1,000 miles an hour is exactly the same amount of thrust as a 2 kilograms going in the opposite direction. And that's the truth. And that's the facts. And so the fact is that when they went to the moon, they didn't use this formula. When they started shooting things out of their lunar modules to make it land on the moon, when they were shooting stuff out of their spaceship, they were using MV. They weren't using this thing because they wouldn't land it right. Because it's going to give you completely wrong answers. Anyway, but yeah, I'll go over some other stuff. So I'll take a pause, and we'll get to that. I'm looking for this one. I'll be back. All right, I'm back. Let's see. So there's lots of thought experiments that are done, but there's no actual experiment. So it's the simple one that would tell us all the truth would be is that they could, the simple experiment would be you take, two trains, okay, and you just invert their mass to velocity ratio. So you just say this one was 5 tons and it's going 10 miles an hour, and you just make this one a 10-ton train going 5 miles an hour. Now they have the same momentum, okay, by logic. So the MV part is exactly the same, and now we're just saying what part am I squaring. In one case I'm squaring the 10, the other case I'm squaring the 5. I'm going to get very different answers for their energy. This one's going to have 1/2 the amount of energy of this. Now the truth is they have no physical experiment. So we're just saying about, it doesn't have to be trains, it can be dogs, it can be anything moving with these opposite inverted mass to velocity ratios. And we don't have in the hundreds of years since 1652 or whatever, we don't have a single experiment, a single physical experiment done by physics, done by scientists, to demonstrate the fact that this train actually has twice as much energy. Now, momentum says they're going to do the same thing, and when they hit a wall, okay, they're basically, or let's say when they hit clay, right? Now, we don't want to say clay, we don't want to say a wall. What we want to say is if we attempt to collect the energy, that is, we attempt to do something equal, like let's just use bowling pins to slow them down, right? Bowling pins are essentially just friction, and we can have the same amount. We'll just calculate how much momentum each bowling pin got. You'll find that both of them will give the same total amount of momentum to bowling pins, right? So that would be a way of measuring. Another way of measuring is put a little electric generator on the wheels, right? The faster the generator turns, the more force it applies against it. So it's going to slow this one down very fast because it's going to be applying a lot of torque against it because it's going to be spinning very fast. And the opposite will happen here. It'll slow down slower. But the fact is, this one might take longer to slow down, but I mean, not longer. It might take more distance to slow it down. But the fact is they'll light the same number of light bulbs. So if I count how many watts I get out, okay, and a watt is the same as a joule, if I count the number of watts they can produce in a generator, I would argue that it's quite obvious they'll both generate the same amount of wattage. They'll light the same number of light bulbs because mv squared is the right answer. That is what energy is. So we have no evidence, just none, no experiment ever done. So just understand, this is core of their physics. This is a fundamental assertion, and yet they don't have a single physical experiment demonstrating it. Not one experiment showing us a bullet, okay, coming out of the gun, doing 2,000 joules worth of work. 2,000, it's a lot more. So we're saying the gun only got 2 joules of energy. So the gun barrel is only going 2 joules this way. The bullet's going 2,000 joules this way. And they've never done the experiment to say, well, let's try to collect that. Let's try to light light bulbs. Let's try to do something to collect the energy to see if that insane ratio is true. Okay, that the bullet actually will do 1,000 times more work in the world. It'll move 1,000 times more atoms, a distance, a velocity. It'll knock over 1,000 times more bowling pins. I can knock over 1,000 times more bowling pins with the bullet than I can with the stock of the gun. And we don't have a single physical experiment. Nothing to use. Nothing for me to point to. Nothing for you to point to as an opposition person saying, oh, it must be true, it must be true. You don't have a single experiment you can show me, okay, where this extra insane amount of energy is collected. Nothing. All right. So what else do we need to say? Before moving on, we'll just play some Professor Lewin and call it a day. We'll have to because we got no choice. Even the simple example again, like the bowling ball. So you have 2 bowling balls rolling down the bowling alleys. One ball weighs 8 pounds, is going 20 miles an hour. The other ball is 16 pounds and it's going 10 miles an hour. The fact is their theory says this one knocks down twice as many pins. The 8-pound ball knocks down twice as many pins as the 16-pound ball. That's their theory. And they don't have any evidence of it, though. No professional bowler does this. He doesn't sit there and use an 8-pound ball and just throw it hard. The same energy. Throw it with the same amount of energy, he would get the same result. That's conservation of momentum. But some of them don't believe that. They believe that, when you go from the 16-pound ball and then you pick up the 8-pound ball, it weighs half as much. Let's understand, half as much, a huge decrease in its weight, that you can only throw it 1.4 times as fast. So you can only throw it 0.4 times faster. That 0.6 is lost. You somehow you lost 30% of the power to throw the bowling ball. that you can only make this one go a little bit faster. You can't make it go 20. You can only make it go 14. That's what their argument is. So their argument is when you pick up, you go from a 16-pound ball that you threw 10 miles an hour, then when you pick up the 8-pound ball, you can only throw it 14 miles an hour. That's their argument to defend this mush. Now they have no, like I said, no physical experiment. They have no person actually picking up volleyballs and throwing them to demonstrate any of this. They'll just assert it as that's the absolute truth because my formula says so. And I'll show you another thing their formula says that can't make any sense to anybody rational, but they say it. Okay. Professors at colleges say it. And it can't make any sense. So anyway, all right, so we'll do that next. Which means now, I guess, from your perspective, it will mean pretty much now. Yeah. Alright, should be back. And so this is just really talking about the energy duality. Okay, they got these two ludicrous things, momentum and kinetic energy. They're ludicrous combined. So it's oil in water. You can't combine these two things. You can't have a duality. They can't coexist. One of them is the right answer, one of them is the wrong answer, and that's logically a mandate essentially here. You can't have any notions of conservation of energy in the universe if you're switching between momentum and kinetic energy as the definition of energy in the universe. It just can't make any logical sense to somebody who's logical. This duality will fail. It can't be maintained. It's so illogical. So they talk about conservation of momentum. Now, everybody who believes in the 1.4 theory, the theory that you can't throw things twice as fast with the same energy, if it weighs less, half as much, you can't throw it twice as fast because you can't manifest any more energy than you were given to start with. Okay, that is what you threw the 16-pound ball with. Anyway, it's just it doesn't make any sense. Okay, so anyway, so in this video he'll talk about the conservation of momentum. In another video he'll talk about the conservation of energy, and it can't make any sense because you can't conserve two opposite amounts. The answers are not the same. Momentum says 50, kinetic energy says 100. In the bullet example, kinetic energy says 2,000 and momentum says 2. Huge differences in the answers. Alright, so we'll just play this clip for the piece that's important. Now in this experiment he's doing something that, it makes perfectly good sense. He's talking in terms of momentum, so he's defending Newtonian physics here. And so he's just basically saying if I'm going to put a force between two objects, an explosion, that if this one weighs twice as much, it'll go away twice as slow as this one, because momentum will be conserved. Alright, because momentum is a real thing. It physically works in the universe. It's what made Newton famous is the fact that it works as an answer in terms of understanding how things move in the universe. Momentum works. That's why Newton was famous, is because it worked. And yet kinetic energy is screaming, somehow it doesn't work. It really doesn't work. It really does. And there's no reason for you to believe it really doesn't work. They don't have a single experiment they can show you, except a clay experiment, and Stephen Bro couldn't make that work, to show you that somehow this is correct, that we need to believe in kinetic energy.
Interesting, because now you really begin to test the conservation of momentum. The momentum before is 0. I burn the wire, momentum afterwards is also 0.
So let's understand, this is part of the logic problem, right? Every student in this classroom should say, what are you talking about? The momentum is 0 after the explosion. It's retarded. We know there's a ton of momentum going that way after the explosion and a ton of momentum going that way after the explosion. And if it was a regular explosion, you'd say, oh, there's momentum going that way and that way and that way and that way. And there's momentum all over the frickin' place. What do you mean the momentum is 0? So obviously, this has a whole theology built into it that if you don't understand the throne, like this is the God throne and this is the Holy Ghost throne and this is the Jesus throne, that you can't understand how it all works. But it's illogical right on its face to sit there and tell me there's zero momentum, that nothing changed. So something substantially changed, okay? Energy that was trapped inside a little tiny chemical all of a sudden is now flying. Pieces of it are flying in directions into space. It's no longer trapped. It's a completely different universe now. Fuck. I mean, it's just so bad to use this illogic that because one piece is going this way, it cancels the piece going that way. But if it's kinetic energy, this piece doesn't cancel that piece. I mean, we have duality rules. Rules will just change the fundamental mechanical rules. Left, right doesn't mean left, right anymore. This is left, right. Or that's left and that's right. No, come on. We already know that we're going to have one set standard here, okay? And we know that the kinetic energy is moving in the same directional, it has the same vectors of direction that momentum has. It's MV, for fuck's sake. The variables are exactly the same. How can you sit there and say one of them has a direction, one of them doesn't?
But the velocities, I erase this. V2 prime divided by V1 prime equals M1 divided by M2.
Now, to defend kinetic energy, you basically have to say that's wrong. Okay, that just doesn't happen in the real world. That there is no proportional relationship, inversely proportional relationship between mass and velocity. He's going to put a box around it, and then there's no way he could put a box around it and then start talking about kinetic energy, because it's not true anymore.
And so twice the mass will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum.
Right, and logically you're supposed to believe that in one case nature completely failed to push it. 1/2 of the energy of the explosion. So unless you believe the explosion couldn't explode equally that way and equally that way, that there isn't the same amount of stuff going this way as there is this stuff way, right? So let me just turn into just to eliminate any notion that you can change this somehow. Let's just put bowling pins around the explosive first. So I explode something. The bowling pins start leaving. The explosion was symmetrical in the sense it's going to send pins going this way with the same momentum, velocity, and mass as it's going to send this way. So there's no doubt about what's leaving the explosion is a certain amount of momentum, because I've converted into pins. And now the pins are going to hit carts. How do you make an excuse for why the pins that hit the heavier cart couldn't move it, and yet the pins that hit the lighter cart could move it? I mean, what's your logic going to be? That half the energy of the pins hitting didn't go into the cart? Yet if I do the calculation, that if I add up, if I say the pin has a weight of 4, okay, and it has a velocity of 10, and it hits the cart, well, clearly the cart did collect all of it, because the cart is actually going to have the momentum is going to be transferred equally to this cart and this cart. So somehow I'm going to transfer the moving pin energy, the amount of momentum the pin has, is going to go in. There's no doubt about it, okay? Mechanically, he's conceding all of the energy got into the object. All of the momentum of the explosion got into the object. The pins hit, it collected the energy, and it moved. So where are you going to get this excuse that somehow, well, wait a minute, no, it only has 1/2 the energy? How are you going to make it happen? You're not. So I'm just saying maybe that's the way to do this, is I'll just detail 50 pins going this way hitting a cart and 50 pins going this way hitting a cart, okay, of the different mass, and just point out how the exchanges are guaranteed because this end number is going to be the right velocity. You can't acquire the velocity without the pins having hit you. Okay, so when I take the velocity of the pins and let's ignore the mass and just say we're just really transferring units of velocity. Okay, and I'm going to get a unit of velocity, a unit of velocity, a unit of velocity. They're both collecting the same units of velocity, technically, proportional to their mass. Well, anyway, But I mean, how do you believe this nonsense? So anyway, this is where he says you can't finagle.
Nature has no choice. Nature can deal with kinetic energy one way or another.
So right there, shouldn't we just say, if I'm sitting there listening to him, okay, so nature can fuck up kinetic energy. You can just screw around with it. You can make the numbers go anywhere. So yeah, there can be 2,000 joules going that way and 2 joules going that way, and I don't have to worry about it because nature says, who cares? Kinetic energy can be irrational. I mean, that's what he's basically saying. Kinetic energy can be irrational. But momentum? No, it can't be irrational. You can't screw with it because it's so easy to follow momentum. The MV part can't be screwed with. If you start squaring things irrationally for no good reason, right? You have no evidence. You have no good reason to put that 2 over the V. You could put a 3 there. You could put a 7 there. You could put 500 there. You could put any irrational number there and change reality, but you have no reason to do it because momentum works. It always gives you really good answers. That's why Newton was famous. That's why Newton was buried as a god, you know, in the bottom of a church or something, I mean, you know, Windsor Castle or some other, whatever. He's buried as a god. Okay, it's because he didn't get wrong answers. It's because he got right answers.
But it cannot finagle momentum.
So again, there's any point in having this conversation, right? The physics professor is overtly telling you momentum is good stuff, really works. And kinetic energy is finagly, you know, wimpty bimpty hoopty doopty. Okay, he's telling you right there. Now later he's going to pretend kinetic energy makes sense, but even when he starts talking about rockets, he's going to say, yeah, the same gallon of fuel gives you 5,000 joules of energy when you're already moving. You know, when you're going pretty fast, I get 5,000 joules out of this gallon of fuel, but if I'm not moving as fast, I only get 2,000 joules. Even though the rocket engine is burning exactly the same way, it's throwing the same exact amount of crap out, somehow it's so much more. It's more energy somehow because I'm already moving. Nonsense. Can't make any logical sense. All right, and that brings us to the paradoxical video. Okay, the one that just, there's no good answers here, and nobody's providing anything like a explanation. It just can't make any sense. You've got to know the physics is broken. This isn't right. Something's broken here. It's broken. And why are you defending physics? It's overtly broken. You can't explain it. It doesn't make any sense. And yet you're going to defend this as being well thought out, rational science, when it makes overtly no sense.
Completely inelastic collisions.
Sorry,
are the same. And there's an elastic collision. This one will stand still. And this one, v2 prime, will have a velocity v1.
So this is just a case, another cart example. So he just bangs one cart into another cart of the same mass. Somehow it works just fine. Everything transfers and you get the same out that you put in. Same momentum. This is going 50 miles an hour. The new cart goes 50 miles an hour. This one stops. Makes perfectly good sense. All right, now, because he took the kinetic energy formula and the momentum formula, okay, and put them into, unnecessarily complicated derivatives, and then he combines the two derivatives to come up with a new formula. All right, so it's a bastardization of combining, of pretending the duality isn't a conflict, and combining the two formulas into a new third formula. And that new third formula says this preposterous thing, this thing that just can't make any sense to the reasonable person.
So that's a prediction. The second case, I bounce one car onto another one which is twice the mass, certain velocity, which I don't know what it is.
So he's just saying he's pushing it. So each time he might push with a little more energy, a little less, and all we're really talking about is whether, what proportion of that velocity will be transferred. So we're just talking about what percentage.
And now, what are we going to get? So mass m1 is half the mass of m2. So this is a 1.
So this is his wacky derivative up here, taking the velocity, the momentum formula, and then combining it with the half, so you see it here, half mv squared, combining it with that wacky formula to come up with this third derivative.
And this is a 2, and this is 3. 1 minus 2 is minus 1, divided by 3 is minus 1/3.
All right, so I don't know if we should play all of this. I mean, he puts springs on the carts to make them more elastic. They're already got metal edges. So whether you put rubber on them or something else, you know, to make them more elastic. I mean, so this is sort of the part of the problem. So they have a formula that applies to an elastic, collision, and yet they have this bizarre definition of what elastic actually is, because apparently steel hitting steel isn't elastic. You know, as much as they say it's perfectly elastic, it apparently isn't, because the experiment won't work. So until I put a spring on the objects or I put rubber on them, I can't make them elastic. So right here we have another, what is that? Is that logical? Can anybody make sense out of that? You have a word called elastic, you use it, you apply it to different things, and yet the things are substantially not the same thing. They're not elastic in the same way. So it's a pretty horrible abuse of language.
So number 1 comes back. No surprise. If you bounce a lighter up.
So he just says no surprise, but it is to a physicist, okay, bouncing back. You'd say, well, why doesn't the energy just keep going forward? Why is the energy changing direction? It's a pretty radical thing for the energy to change its direction. You know, you have momentum in a direction, and you're saying, well, all of a sudden it just switches direction. So, I mean, it's a pretty radical outcome. And there has to be a physics explanation for it. You can't just say somehow it just does it. I mean, it's not a little thing. It's something that needs explaining.
Object of a more massive object, no surprise that it bounces back. So that's minus 1.
You're right. No surprise intuitively from life experience, but big surprise from physics. Because physics, if you look at it, it tends to say you can't destroy this way. So this way is going this way. How do I make it go that way without destroying this way? How can I convert this way into that way without any evidence of the conversion?
Third, and when we look here, we have 2 times 1 divided by 1 plus 2 is 3. That is plus 2/3. So number 1 will come back with a speed 1/3, which of course, since this is sign sensitive, we get 1/3 v1, and this one is plus 2/3 v1.
Right, and so logic tells us in all these other experiments it's always half. So somehow it's going 2/3. So I've doubled the mass, and instead of getting half the velocity, right? So you put one velocity in, double the mass, you get half the velocity out. Makes perfectly good sense. Conserves momentum. Here, momentum, no consideration, right? Because now I have 2/3 the velocity in this direction. So I've doubled the mass, and now I have 2/3 the velocity, which means I have 16%. Realistically, that's the number. You know, with the difference between 2/3 and 1/2 would be 16, percent. So 16% more energy than I should have, than should be possible. I shouldn't, to conserve momentum, it should not be possible that I have 2/3 in this direction. And logically, that something going this way, 50 miles an hour, doesn't care if something's going 10 miles an hour that way, right? I mean, that's not going to change 50 miles an hour this way. So the fact is, I put 50 miles an hour into the experiment this way, and I'm going to get 66 miles an hour out. And that's what's happening in this experiment. 50 miles an hour in, and I get 66 miles an hour out if it was the same mass. So if I give it the same momentum, so I gained actual physical energy. Now, yes, this one went in 50 and I got twice the mass, is coming out at 34. Okay, miles an hour. But 34 miles an hour for twice the mass is more momentum. So I've increased the momentum. Increasing momentum is the same as increasing pressure. Pressure lifts things. Pressure, applied to a lever pushes things up. The pressure is energy. So if I'm increasing the pressure that the object will impose, essentially increasing its weight, okay, its force, the F word, okay, the force of the thing going in, the thing coming out is coming out with more force, more energy. That shouldn't be possible. It can't be possible. And the only way it can be possible is if there's some mistake somewhere, right? Somewhere there's a misinterpretation of reality. Either there is such a thing as free energy. I can just increase the energy. I can just keep doing the same experiment over and over. I can increase it 16%, then increase it 16%, then increase it 16%, then increase it 16%. And then I can just reverse it in the opposite direction. And then I can just keep going, and I can create a perpetual motion machine that generates energy. Which we all should say, well, that can't happen realistically, can it? I mean, for hundreds of years, we've not seen this obvious way to generate free energy. We've been wasting all of this time pumping oil and doing all these things when all we have to do is bang a light thing into a heavy thing and we could just keep making more and more momentum. I mean, I would know, and I think you know, there's got to be something wrong here.
That's the prediction. And the way we're going to measure it is by measure the time for the objects to move over a distance of 10 centimeters. No matter how long you see these cars to be, there is here a piece of metal which is 10 centimeters long. It goes through a slot with a diode. We have one system here and one there. And during this 10 centimeter...
Sorry, unnecessary details, but, whatever. He's validating how he's doing the experiment, which is fine. But, again, I'm just going to argue, we know something's wrong with this experiment.
Movement, we measure the time. We begin when this piece of metal enters the diode system, and we stop the time when it leaves the diode system. And each one of those cars has this 10 centimeters.
He's just measuring velocity. Okay, it's not that complicated. So you could take a video of the experiment and measure velocity just by putting, frame rate and a graph, and you could measure the velocity. Lots of ways to measure the velocity.
Metal plate. So the way we're going to do this is by measure timing, of course. This velocity will give me a certain time, and this velocity will give me a certain time.
And those will be variable based on how hard he pushes the initial. So the initial velocity going in, the initial momentum, might be 40, might be 70, might be who knows. And we're just talking about percentages.
Whatever comes out, you will see that on this timer. Then, T1 prime
we really don't need this.
In this case, it stands still, so it must be 0. And T2 prime must be the same as T1. So these two numbers you should be able to compare directly. What kind of uncertainties do we?
So one object stops, one object moves. Okay, so let's just skip ahead a little bit. I really don't want to, deny him his argument, but there's a point in here where he describes putting springs on the cars, and that's the point where you say, there's springs on it. Yeah, maybe they're doing something.
So this one goes back with 1/3 of the speed, so it will take 3 times longer to go 10 centimeters. So I'm going to multiply this time by 1/3. And
right, so he's saying 1/3 the energy will come back, 2/3 will go forward, and then you have 100% of the velocity. But the key is the stuff going forward is going forward with twice the mass. So it's a huge increase in your pressure because now you've increased your momentum. So there's more momentum going this way. So somehow you start off with a certain amount of momentum, 50, and then you sent an extra, it turns out to be 16. So you send an extra, I could say 25 and 25, but realistically it's only 16. So you start off with 50, you send 16 going this way, extra, right? And you send 16 going that way. and you say, well, those two canceled, so I won't pay any attention to them. What do you mean they cancel? They don't cancel. You can't cancel energy. Okay, there's no on energy. You know, it's and there's no anti-energy. So the fact is that, you know, our momentum, for example, you can't do this playing games with, because it's going in the opposite direction. It undid what's going in that direction. So the truth is, in the experiment, you start off with a certain amount of momentum going this way, and you have more momentum going this way after the experiment. That's more energy. It doesn't matter if a zillion joules went this way. You can't undo. You have more energy going in this direction. You know, making some argument about how fast the gun barrel is going somehow cancels the bullet is retarded. Okay, you can't cancel the bullet.
Whatever comes out should be the same as this. So let me move this up a little. T2 prime. The speed here, the forward speed, is 2/3, so it will go slower. So if I multiply this time by 2/3.
Understand, it'll go slower than the initial, okay, energy that went in, but it'll go much faster than the half of the velocity it's supposed to get. It's only supposed to get half, and it's getting 2/3. It's only supposed to be able to go twice as slow, and that's, you know, that's what it's supposed to do. It can't go more than half the velocity to conserve momentum. So clearly momentum's not being conserved.
Then I should be able to compare it with T1. And all of that, all these times, I think, will not be any better than roughly 2.5%. Except if we are a little lucky. Okay. System is up. Timers are up. Timers are up. This will be the time T1. This will be the time.
So that's the initial thing he pushes. This will be the what's going that way, and this one will be what's going that way.
Time T2 prime.
The
And
heavy
this is the
object,
one when the object bounces back.
that's the
So this
light
is
object bouncing
T1
back.
prime.
Okay, go,
You
go,
won't
go.
see that it is negative. It will go back through the same slot. And the electronics is arranged in such a way that when it goes back through the same slot, that it will initiate this time.
It won't be negative because there is no such thing as negative momentum. It's retarded.
I will zero them. First you have to tell me whether they are working. I will just let it go through this slot. This one working. Tell me that this one is working. Speed. And this is the one that we're going to give a...
Alright, so we're missing out on the spring thing, but you can obviously see there's little springs, the rubber, the metal, little bent metal, some kind of mechanism, a spring. He's conceded he's put springs on the metal, so the elastic machines, he's had to make them more elastic. Okay, because they're not elastic enough. Even though they're describable as the most elastic you can get, would be like a steel ball. But somehow, no, that's not the most elastic.
velocity. You ready? I hope you know what you're going to see. This one will come to a halt.
So they're obviously little metal, you know, bent metal. Okay, so it's springy. So it's the same as saying like a piece of rubber. It's something that can be compressed and will expand.
And this one will go on. They have same mass. There we go. This one is indeed coming to a halt.
There, same speed, blah, 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 quite obvious. Okay, let's move along.
Which has twice the mass. It's important that I zero it. And now this one is going to come back. So you're going to see this one come in, give you the time here. This one goes through here, gives you the time here. This one will come back, gives you the time here.
Right, now so if I had an explosion between these two objects, right, what I would get is this one would leave twice as fast as that one. It wouldn't be any 2/3 thing, okay? You wouldn't get 2/3 going this way and 100% going that way. That wouldn't happen. So something's wrong. Something's inconsistent, really inconsistent.
ID 0. Okay. You ready? Yeah. There we go.
All right, so there's no denying the numbers. The numbers are saying 375, that's the one leaving at 1/3. Okay. 186 is obviously not 246. So it should have been 2. The initial velocity is 123, which means half that velocity would be 246. And obviously 186 is much faster than 246. So it's obviously 2/3 is going, and it really shouldn't be doing that. Shouldn't be any place to gain this extra momentum in one direction. And the fact that it exists is a paradox, because if I just keep doing this over and over again with each experiment, with each iteration, I just keep making the 2 mass card, I make hit a 4 mass card, then a 8 mass card, then a 16 mass card, then a 32 mass card. And each time I do that, I'll gain 16, okay, joules, let's say, out of 100. I'll gain 16% more energy. So with each experiment, 16% more, 16% more, 16% more. All right, so you can see it's going to be double in just 3 or 4 iterations. I've doubled my energy, and I could just go back the other way, and I could go this way, and I could go back the other way, and I could just keep that going forever. But I could go back the other way with something like a lever, for example. So that's what. So anyway, huge paradox. Doesn't make any sense. Nobody's explained it. It can't be explained, frankly, without conceding free energy or he did something wrong. Because, I've already explained that the spring is what's causing the energy going back and the energy going forward. If he didn't put the spring on, he wouldn't get these results. The spring is compressing, then it's releasing its energy after the energy's been transferred. So the 2 mass object actually got moved half the speed. It did what it was supposed to do. It moved half the speed, but the spring compressed, released, which gave it the extra 1/3. That's why it's leaving it 2/3, because it gained the extra 1/3, and the 1/3 going the opposite direction happened because the spring made it happen. So the spring did 1/3 this way and 1/3 that way, on top of what was already there. Now, that explanation works, but that explanation basically tells you, yes, it's free energy, so let's just make the free energy machine. Why are you people waiting? Why haven't you already done it? Why don't you just make the free energy machine? Obviously, we can't use an air track because that takes, that's consuming a lot of energy. So you have to use, pendulums or some other kind of object that takes away friction substantially. But you have 16% to work with. Most frictions and most experiments might be 2 or 3%. It's not a huge amount of friction. So yes, your 16 will be cut down to 10, but you're still gaining 10% with each experiment. All right, anyway, so this gives me an excuse to talk about levers, and that's what we'll end on. But it's an overt paradox. It's sitting right there in front of you people. It's sitting there right in front of physics, right in front of science. Nobody wants an explanation. You don't need an explanation. You don't need to know, how did it violate the momentum rules? How did it create more momentum in one direction? How is that possible? You went in with momentum in one direction. You increased the momentum in that one direction. All of the momentum was going one way. None of it was going that way. So how did you convert some into that direction and extra in that direction? More than you could, conservation of momentum allows. Clearly more. All right. So to make that a perpetual energy or a perpetual motion machine is just the simple idea that you would just use a lever, a balanced lever. You just sit there and have the bang, bang. So this is a 2 mass, and this is a 4 mass, and this is an 8 mass. Okay, so you're just doing the experiment. So 16% here, 16% You have to have your initial, yeah, well, 16%, 16%, 16%, 16%. And then you have it push on the lever, and you just have it push this object all over again. Just do the experiment again from this direction. You'll hit with more force here, like, you know, you started with 10 joules, okay, you'll hit here with 100 joules. All right, obviously you'll start here with 100 joules. That means you'll have 1,000 joules here, you know, and you'll just keep doing this, increasing over and over and over again. Obviously some losses, but, you know, they'll be tiny, and you'll just keep increasing it. Every cycle, it's 1,000 joules, then it's going to be 4,000 joules, right? Let's see, 1,000 in, increases to 2, 2 to 4. Yeah, so 4,000, you know, just keep increasing. You just get this insane amount of energy out of this machine. Because of this, you know, the lever can do the switching of the direction rather efficiently. So levers explain, in some sense, how you know, are great conversion devices. You want to convert motion, levers is the way to do it. So if I had a lever, and you know, here's the pivot, and I put a, let's say I put a mass on it here, okay, 10 pounds, and I put 5 pounds way out here, okay, so 5 pounds way out here, right, twice the distance, let's say that was, all right. The weight balances, right? The scale says they're the same thing. This side over here, this 10 mass, says this 5 mass is the same as me, right? It's not the same. So what's changing? Well, what's changing is this thing is swinging, you know, as I've talked about in other videos, things are bouncing in gravity. And the bouncing is this huge distance, and this is a much smaller distance of bounce. And so that's the disproportion. This one has greater velocity, because in the same moment of time, this will move more than this will move. So any movement, any jiggle, this one's going to be going twice as fast as this one. So as the scale is attempting to balance, this side is moving twice as fast as this side is. Twice as fast means it's twice as much energy. Okay, so, you know, by momentum, it's twice as much momentum. And momentum is pressure, is weight. So every time it moves, this one's applying twice as much momentum as this one is. Okay, because of this, because the velocities of the two are exactly, this is just as much as this is 1/2 the weight, this one is 2x the velocity, okay? And this one is 2x the velocity, I mean, it's twice the weight, 2x the weight, and it's 1/2 the velocity, you know, because of the lever. Because the lever, you know, the outside stuff swings much further in the same amount of time the inside stuff moves. The same, you know, it moves less distance. You could use distance as an argument, but obviously distance in this case is velocity. So that explains the lever, and explains that the lever will work. So everybody knows that the levers work. So if I did a lever experiment, okay, where I threw, you know, if I sit here and make this lever and do this, I put a 5 mass object on here, and then I have a 10 mass here, and I drop it. Okay, so now it has a velocity. I say, so I got 10 mass, and I got a velocity of, let's say, 5. What's going to happen here? Now, their theory, the people who say kinetic energy is real, and it's defendable, and it's conserved, and it makes sense, and springs can't do this, and springs... The people who are defending this preposterously silly theory with their 1.4 crap, right? They're going to say that somehow the lever is going to destroy, you know, momentum, and somehow this thing is only going to, it's not going to be able to leave it at 10. So here, this one's a 5 mass. Let me put them in the right order. 5 mass. Okay, and they're going to say it won't leave at 10. Okay, it'll only do the 0.4 thing, so that would be 7 or something like that. It'll only get to 7. It's going to lose 1/3 of its energy. 1/3 of the energy somehow won't be able to go into this thing, and it won't go what you would expect, which is 5 will go 10. Okay? So it won't go 10 miles an hour. I think you know, and I know, the lever works. Okay? This comes in 10, 5. This one's going to leave 5, 10. Alright? Levers work. They don't fail. This one can't tell that this one is... This one can't see this one and say, I see that you're only a 5 mass and you're trying to trick me. It sees it as if there was a 10 right here. Well, that's not exactly... I'll just move this over just a little bit. Alright, the fulcrum. So the same distance, same object, 10, 10. It'll go away at the same speed. We know that. We know there's no way that this lever knows that this is a 5 over here. It thinks the 5 is a 10. That's all it's seeing. It's seeing the same thing as the 10, and it's going to deliver exactly the same energy it would deliver the 10. It's going to deliver the 5. The lever is a stick. It doesn't know anything. It doesn't know it's supposed to not allow it to happen. It's supposed to bend or do something silly. It doesn't know it's supposed to do any of that crap. It's going to deliver the same momentum. It's going to give it the 10. So why are we... This is called a logical proof. I mean, how can you people keep believing something that just isn't logical? So I end with that, okay? You got the Professor Lewin paradox sitting right in your face. I've got nothing, in 2 or 3 months now of talking about it, nothing as a rational explanation why it makes any sense. And again, I can just keep pointing to you to things that in the real world have to be true. I can't break the lever. I can't sit there and pretend that that the 10 object somehow is... If I put the 10 object here, I get all of the momentum. I put a 5 object here, I don't get all of the momentum. Where'd it go? Where's the momentum that didn't make it? Come on. All right. I mean, it is true that if I put an elephant on one side and then I try to hit this side with energy, I'm not going to be able to move the elephant. I'm just going to create a balance that's going to, things will hit and they'll flip off. So that's not going to work, obviously. But I have to make it all very elastic. But anyway, that still doesn't explain. You still aren't accounting for why it can't move a lighter object. Lighter objects are easier to move, not harder to move. That didn't work. We'll try that instead. Well, that worked, but I don't know if that's where I want to be either. Well, anyway, I'll just play with this because I can. So, I'll go all the way back to this one. All right, there we go. Anyway, so till the next time. Enough of a video. Bad history, no experiments, crazy duality logic. The formulas they're not deriving them into the simpler form, they're deriving them into more complex forms. F equals change in momentum over time is the simpler form than what they're deriving it into. It doesn't make any sense. You're not trying to find the more complex formula. You're trying to find the simplest one. It's already in the simple form. I mean, I can just change it to F equals mv over the unit of time. If I make the unit of time the total change in momentum over the total change in, the total amount of time that the change took place in, then I just have F equals mv. That's the simplest form of the formula. That's Newton's physics, and they shouldn't be allowed to do this to Newton, just like they shouldn't be allowed to do what they've done to Einstein and Schrodinger. They shouldn't be able to put Newton's name on a formulation initiated by his worst enemy in life. I mean, that's what makes this even more disgusting. It's bad enough if Leibniz was somebody who lived after Newton, if the whole thing happened much later than Newton and has nothing to do with Newton. But the very fact that this is a formula created by his worst enemy in life And to call it Newton's physics, to say Newton's worst enemy was correct, and then to say it's Newton's physics, that's really pissing on the dead. And Newton doesn't deserve to be pissed on. So it's criminal for lots of reasons. It's illogical. It's untrue. This is not Newton's physics. This is their physics. Kinetic energy is not Newton's physics. It's some other physics, but it's not Newton's physics at all. Not anything like Newton's physics, not similar to Newton's physics, not a derivative of Newton's physics. That's all just garbage. And it's even worse that they do this, where they're putting Newton's worst enemies' theories in Newton's mouth. That's really cheap. Oof. So anyway, it's just nothing good here. There's no good story. This is the diagram of stupid, and evil. It's just, there's nothing good here. There's no good science here. Nothing. Just nothing to defend. Forgot the, hit the button thing. So this has been a DraftScience video presentation. Sorry for the length, it's just part of the price you pay. So I do have 3 videos in the description. I've been around for a while. Photons, gravity, energy. Making this argument in a lot less time. But whatever. This is what it takes. I mean, the details are important, and they should be talked about. Truth.